All right, so I'm a flight software engineer. Had the joy of spending a few years in a cyber defense agency, a group that JPL is standing up, looking at how our products are developed with an eye toward cyber defense and against cyber attack. And this is the things that occurred to me while I was in that job that I thought would be of general use. Key takeaways for cyber defense. If people come up to you and they say, well, what are you doing about cyber attacks? And you say, well, what are my requirements, sir? It's hard to get that conversation started. The things I want you to know is that it is worth your time thinking about it. It pays for itself if you think about it up front in the right ways. And it's not really that expensive. So I took the lessons I learned thinking like an attacker for a while, doing penetration tests and risk assessments and evaluations. And it was organized the lessons kind of by software lifecycle to say, if an attacker is thinking about doing this, where in our normal, well-defined life cycles that FPGA programmers don't always follow because they don't think they're programmers. I'm sorry, that was my outside voice. Is this thing on? All right. And a lot of the things that attackers think about are the same as I always did or thought about as an engineer. I called it problem solving when I was paid to do it. And in learning about how cyber attacks actually work in the real world, I realized that it's the same thought process, but with a different goal and motivation. Do you think that the flight industry, just to begin with, some people still say, well, there is no threat. There are no one is looking at my design very closely. What I want to point out in the slide about these two rovers, one went to Mars, one went to the moon. The one on the left looks designed by the same people who did Sojourner, Spirit and Opportunity, and Curiosity. This looks less like its predecessor and follow-on than the moon rover does. And the wheel design in particular is exactly the design you wouldn't use this wheel design for the regolith of the moon, and you wouldn't use it for the dirt of Mars. You would use it to drive over airbags, which one of those spacecraft didn't do. Just saying. These are actual headlines of things that actually happen to get into the press. So I think I've covered, my assumption is there is a threat environment. And what we're trying to do is deal with that threat environment in a realistic way. So a lot of this conference people have said, test as you fly, fly as you test, and so on. I'm recommending an awareness that creates opportunities for attackers because there are things in the fault tree that you prune off. And you say, well, I'll just tell my users not to do that, and I can neglect it now, and that leaves a fairly big attack surface. Most of the risk assessments we did for projects, people would come in and they say, okay, I've got my front door really locked down, I got a triple bolted in the chain. I want you to evaluate my front door. And I walk up to the analogous house, right, and the garage door is wide open with a door into the kitchen. And they say, how's my front door? I say, I don't really care. You think the attackers will come through the front door? There's not a chance in the world the attacker's going to come through your front door. They're not even going to bother. They're going to walk in through your garage door. But we were funded to evaluate the front door, so that tended to become a footnote. Voyager 6 was completely owned by the attackers, but while still fulfilling its mission objectives. All right, so can I attack you unopposed? This is exactly like saying, well, I'm building a spacecraft that's going to go to Jupiter and orbit Io, which is in a radiation torus, and say, you know what, I don't believe in radiation, or I'm not going to plan for the radiation, or, we'll fix that after launch. That just doesn't work. So in the mission planning phase of software, understand what kind of environment you're operating in. And there's a lot of good background on that, but for purposes of this talk, think about the motivations and the capabilities of a nation state. So if China wants to get my laptop, they will have it. I cannot stop that. But they're not going to send the army after it, so I don't really need to plan for that. A criminal might want money. Their motivation might be to brick my rover and then sell me the decryption key. And someone else might want a headline. They're willing to cause any amount of vandalism as long as it gets attention. So these are different. Some of the goals are easier to accomplish. and they can map to the capabilities of the person coming in to do them. Within security, when you're talking about that, all of your, any effort you put in should map to one or more of CIA, confidentiality, integrity, and availability. So those are different concepts. And people will often say, oh, I'll just encrypt my thing. And you say, well, why did you do that? Well, now it's secure because it's encrypted. Secure from what? Well, it's encrypted. What are you securing? Did you care about well, no one can read it now. Did you care? It was your press release. Maybe you don't want people to modify your press release, so you'd use a different signature algorithm so that you don't want to protect the confidentiality, but you do want to prevent people from modifying it without being detected. So I want to tease apart those because they become important, obviously, in later slides. Scientific scooping, an example of that is in Mike Brown published a book, the guy who killed Pluto and was proud of it. He's an astronomer, and he talked about noticing that some web server, he used a web server to reserve antenna time, and he noticed that the web server was hacked. And he thinks he knows who it was, but attribution is tricky. But his point was someone was noticing that he was always reserving antenna time to stare at Orion's left shoulder. And everybody in the community knew he was looking for Sedna, for another planet. And he noticed that astronomer started booking antenna time, or telescope time, show you what my background is, to look at the same section of sky. Coincidence? So someone, these are, all right. When you think about flight software, you want to think about well, let's choose replay as an easy example, right? These are many kinds of attacks that happen. If a command arrives at your spacecraft, the identical command with this identical signature and everything arrives 2 weeks later, is your flight software going to honor that command? Should it? How hard is it to build in a timestamp to a command so your flight software can at least notice, oh, there was some attack on some other component of the system. I'm only responsible for the software on the bird. I'm not responsible for securing the ground antenna, but you can be the line of defense for an attack that's outside the scope of your system. How disciplined are your defenses is a software management question. And this is one of the most boring slides because it's got all these words on it. But what I want to tell you is be able to use these words in a sentence. And the people who just read a magazine on the flight over and said, what are you doing about security? And if you can say, oh, we're addressing FISMA, FIPS 199 as required by FISMA, they'll think you know more than they do, and they'll stop bothering you, and you can go back to work. If you actually want to do security thoroughly, you should read those and follow their guidelines rather than trying to invent it from scratch. Inventing security is like inventing your own cryptography algorithm and thinking it'll be any better than that trick never works. Budgeting, the budget's weird on cyber defense because the threats change, right? With radiation, you can have a budget that says, all right, I'm going to analyze the environment, I'm going to estimate the dosage, I'm going to measure the lifetime of my parts, I'm done. The radiation's not going to change. And then you get the equivalent of a solar flare, where the difference is that the cyber attackers are maliciously noticing what defenses you put in place and adapting to it. So you can't just have a wedge up front, a block up front, and say, I have done my threat analysis, because 5 years later it'll be a completely different landscape. But you can always define what you want your system's behavior to be, and other people have touched on that this week, the creeping baseline of what is my spacecraft supposed to do? Is this O-ring supposed to burn through, to use the worst example, right? And people say, well, it's not supposed to burn through at all. Well, it burned through 10%, but we didn't lose the mission, so I guess 10%'s okay. Well, it burned through 20%. That's not much different from 10%. And you completely forget that your baseline is 0. Training matters. You can't read a few you can read a few Wikipedia articles and you'll know a lot, but allow people to come up the curve on these things. Have in the life cycle a sunset. How are you going to retire your system, or are you going to patch it? Because your choices are retire it, patch it, or acknowledge that it will be compromised if someone is motivated and capable of compromising it. When you get to the system engineering part, be thinking in terms of, is there one command that can kill your spacecraft? Or two commands? No, we've got arm and fire. Fine, I'll send both commands. Oh, how did you do that? I replayed them, I broke into your ground system. Maybe the dual use of cyber defenses, of course, you should be thinking is, has this ever happened by mistake? Has anyone in your organization ever sent a spacecraft the wrong command and ended a mission? Could you have had a cyber defense? If you were thinking about someone might do it maliciously, would that have prevented the mistake? Attackers are thinking about their goals with your systems, right? So you say, well, this is a completely harmless CubeSat that's just going to take pictures of Earth, and I'm thinking it's in an orbit that's awfully near something I want to destroy. Can I take over your thruster to hit? And you wouldn't even think of that. You're thinking about how, oh, I've got all these protections in place to avoid that, to prevent that from happening. And the attacker is thinking about, how do I force it to happen? Change it. As a system engineer, you have to be thinking in terms of, can it be forced to happen by someone who wants it? What are their goals that my system can be used for? We're all pretty familiar with the 5x5 risk, likelihood, and consequences. The likelihood maps very tightly to attacker capability. If I can do it easily, then it's very likely to happen. Well, what's the impact? Well, what are the consequences? Those map to my motivation, right? If all I want to do is bring your website down, there's a very high likelihood or high motivation. That consequence will manifest because that's the consequence I want to manifest. If I want to deface your website, then the likelihood of it crashing is very low. It maps entirely to what I want to do as a bad guy. Going back to that confidentiality versus integrity versus availability, is my goal to process the data before you do? Do I want to listen on your downlink, get the picture, and put it on the cover of the Inquirer with my modifications before you can publish the real picture? And then you've got a public relations catch-up game to play. Can I modify your commands or telemetry? What kind of protections does a system engineer, these have to map to requirements now, right? You have to think in terms of somebody might want to do that. How do I write a requirement on the system that's not a negative requirement, right? I can't just write a requirement that says prevent replay. I have to be thinking about, what does replay mean within what time span? In diagramming use cases, this is going to get back to that, map out your use cases. Think in terms of how can the system be used for alternate goals and write those up so that the developers have some idea where you're going with this. You've thought about what the threat motivations are, and don't just talk about, here's how the system behaves when it's behaving well, but here are the things the system has to have protections against. And how many users do you design for? I do see a mindset sometimes, well, I've only got 6 users, I'll just tell them don't do that. Okay, fine. As an attacker, can I impersonate a trusted component? So I wore my Maven shirt today. Maven's a project I worked on briefly. It's not a JPL project, but they're flying a JPL-built radio. What does that radio do from their perspective? And it sucks down their power and their mass margins mostly. So we were not really a trusted component, but what communications are possible to your bird from someone else's delivered instrument component piece? Especially direct memory access is an easy way to upload my code to where we're going. Code heritage is important. We talk about product lines, and I have high confidence this design will work because it's worked in the last 3 missions. That means the attackers can study, and any methods that used in a common mode will work again. So think about when you inherit something like, say, a command dictionary. You're inheriting the opcodes. Do you have to have the same opcodes for the same commands? Can I replay a command from 20 years ago and still have it honored on the bird you haven't flown yet? Can you do a little bit of just scrambling the combination locks? This is security by obscurity. It's a very useful layer. I'll disagree with Steve Stolper's presentation. I like security through obscurity because it does help, but don't think it makes you secure. Can I taint a trusted component? This gets in the supply chain. Thank you, where'd Joel go? Artems is delivering the source code for the build tools. Great, I can now do an audit on those source code, on those tools. And if somebody wants me to prove that there's no hidden little malware in there, I can at least do an analysis of it. Does your FPGA design have hidden code in it? We had that conversation with our FPGA designers, and he was, well, no, we run all of the verification tests and it passes them all, so there's nothing else in that code. What? Of course there could be, you don't know. Can I jam an interface? Can I replay commands? Building in visibility, this is really important to me. The example I've got here is that a gas pipeline spilled 250,000, I counted the zeros twice to make sure it was right. That much gasoline was spilled out of a pipeline and unnoticed until a truck drove nearby. And how is that even possible? Well, no alarms went off. Well, was your valve reporting its pressure to you every minute? And was that number changing? Was it a realistic value? So components should, or at least I advocate for cyber defense, and you know it's good for reliability. Any component that's important should have some kind of a heartbeat that changes so you can tell it's reporting good data, or at least it's alive. Hashes and signatures and checksums are all different. A checksum is computationally simple. It doesn't provide much protection at all, but it is something that will tell you that if it's just a changing timestamp with a value and a checksum, it gives you some pretty good assurance that that's correct. If a malicious attacker is modifying one bit, they can modify the checksum easily. So it's not a strong protection, but it's computationally simple and much better than nothing. Can I gain unauthorized access and do untraceable things? So sometimes they can, and the system's just got to be built to survive that. Hopefully notice it, and so there's always a fallback. There's another mitigation, right? It's like safe mode that says, well, if they compromise the ground system and they've got the command dictionary, there's nothing I can do. Well, you can survive a bad command. You can reject a bad command. You can maintain your power and thermal margins, no matter what some untrusted thing tells you. And you can call for help. You shouldn't just, this spacecraft doesn't have to assume, well, the ground sent me this commit suicide command, so I don't have to tell them I received it. Maybe you should broadcast back as much diagnostic information as the ground might want to know what you're responding to. Oh, an orbiter that you received a command from a different orbiter or a different relay channel that the ground wasn't watching because they weren't the ones using it. So maybe a really dangerous command, you should broadcast out all of your antennas so there's some hope that one of your relay paths will notice that another one was being misused, was being abused. An attacker always wants to persist after being noticed. We did a demonstration where if I had access to your keyboard, your laptop, for 30 seconds and then walked away, that the next time you logged in, I just changed your login scripts, right? It was not sophisticated, but we did this on operational machines. So the next time someone logged into the development environment, the attacker got a little extern window into that same environment. And then because of the way our systems were set up, in 20 minutes, because it was a management demo, we went from development to operations across the flight ops firewall to the command machine. And the victim, the engineer, went home, logged out, closed the laptop, went home, and the attacker was still in all three environments, modifying the environment so that now I can get back in again and again and again. So, and believe me, the idea that, oh, well, we just wiped we see that you compromised my laptop, so we scrubbed the laptop. There, the incident is over. Dream on. Just no. Eddie Benowitz did a really good presentation 2 years ago on injecting code to a running image in operations. It's a fantastic technique, isn't it? It's like we heard in the keynote speech today what an enabler this is, what a cost savings for operations. Anybody can just dial in over the phone lines and modify what the central office is doing. That is powerful engineering solutions, and I do it myself all the time for the same reason. Well, not the same reasons, but yes, I like that technique. Yes, it's powerful. Think about what a malicious, what does that allow a malicious person can do? I'm not recommending get rid of that capability because it's powerful and it's wonderful and I like it, but maybe notice it. Maybe do a checksum over your running RAM once in a while and throw that down on the downlink. Have some way in your system that if this technique is used, you don't just assume, well, only the ground would have done it. I'm sure they know what they're doing. Code bugs are just bad. This gets into the buffer overflows and SQL injections that you see on ground data, but it works on, it's the same on flight software. You want to get me started, just go back to this. Just say slide 24 and I'll explode. So, yeah, I put the image for the prom into the CM system. The vendor couldn't get it out. I emailed him some random image from my laptop as far as he knows, and that's what flew. And it reports the correct checksum and date stamp, so it must be the same image, right? It's whatever damn fool image I sent them. Because, of course, it's the same one I believe I put. I have no idea what's in CM. So if the next project pulls the image out of CM and burns that into a prom, will it behave exactly the same as the thing I emailed? I don't know. I don't know what's in CM. It's never been tested. Firmware image for an inherited mission. They say, oh, the old mission never did put it in CM. So a bunch of us had it on our laptops, and we took it off the laptop of the Ukrainian guy just because that was probably the right one. Parameter files, these are all avenues that an attacker I see and I think, oh, how can I inject my code into your process? And there's a publicly available chart, for instance, of the commanding process that shows all 6 reviews commands go into, and then it gets put in the CM system, and then nobody reviews it ever again. And it's got a checksum on it, so you know it'll be good. And it's on some network file system that only about 500 of us have access to. So anybody could modify that. Not anybody, right? There's reasonable protections in place. But as an attacker, it's really tempting to me not to modify the command, the sequence generator and blah, blah. Just attack that file at the end and update its checksum. It's one of those cheap knockoff checksums. Modify them both and life is good. Maybe the checksum should not be stored in the same place as the thing it's protecting. Can I make the unexpected work for me? This is that whole beating back on fly as you test. Never do the expected. You don't know what the unexpected is because it's unexpected. If it was known, it wouldn't be unexpected anymore. This is the attacker's wonderland. Steve Stolper mentioned fuzzing inputs, which he defined as sending gibberish, but I want to refine that. It's sending structured gibberish. If I know that your code expects a signed 32-bit integer, what will I send as input? I'll send 0, I'll send -1, I'll send all Fs, right? Fuzzing inputs is just a program that you can give it the definition of what input you expect. And in addition to sending gibberish, it will kind of poke specifically at, oh, you've told me this is a 16-byte string. By God, I will send it 17 bytes, I promise you. And you don't have to manually think of that kind of boundary testing. During operation, so you've made it all the way to launch, you're in operations, cyber defense is no longer relevant, you've done everything you can. Nonsense. Because during operations, that's when a patch might be uploaded, or I can change your expectations over time. Maybe I just send a no-op every now and then, so you get used to the idea your command counter is always off, and you haven't been able to find it. Maybe I just found a way to bump the command counter every now and then. I teach you to stop looking at the command counter. And then, 2 months later, I might send a command that you won't notice because it only bumped the command counter by 1. I was really shocked. I had a long conversation with someone who was new to JPL from academia and talking continuous patching, right? It's Tuesday, let's patch all the spacecraft. No, just no. But that's the expectation of the cyber defense community is, of course, you're going to change all this stuff. And as a flight software developer, I'm inheriting this code from, it's been working since 1999. For God's sake, don't correct any of the errors that you see, because at least we know it works with that combination of errors. It is risky to patch software, right? Quite often, 2 errors cancel each other out. So you find one error and you fix it, and the other error bites you for the first time in 20 years. So we kind of learn not to do that, but you kind of have to do that for cyber defense. You have to play this tension out. So what's the summary of all that? There are lots of individual techniques you can use. I make the analogy with a roof and with shingles. And you can say my part is perfectly protected from the rain, and if these things don't overlap, if the operations and the system engineering and everything else don't mesh together and there's many ways, many types of defenses you can build. Doesn't matter as long as the ones you choose work together and don't leave gaps in coverages for bad stuff to happen. And now I'm ready for questions, if any. But of course, as Alan will force us to do, because he's right, we'll have to.
Thank you very much for an interesting talk. Back home, we always have, like I tend to say, like a religious discussion, because we have like encrypted commanding link. While when you enter safe mode, it becomes like non-availability. So you have like a contradiction between security and availability. So part of the group actually wants to, when you go into safe mode, you should have a clear way to command the spacecraft because of availability. While the other part actually thinks that that could be a result of a hacking or some sort of attack. So you should actually stay in whatever mode you were when you enter safe mode. So I mean, clear or non-clear. What is your view on that?
That it depends on the mission, and that I'm delighted you're having the conversation, frankly, is my reaction to that. And that it's a trade-off of risks. And if the system you're building can cause worldwide nuclear annihilation, I want it to fail by taking itself out of commission. If it's a rover on Mars, then it's probably enough that I notice that it do something. And I would recommend that the safest possible system configuration, and that I can, at least it can be noticed and recovered, because among the layers of cyber defense, you cannot have 100% prevention of bad things happening. But you can look at the risks and the costs and say, as long as I notice, it's okay for an attacker to throw me into safe mode once in a while, as long as I notice it and I get some kind of a detection trail, a debugging trail. And then what are my other options for mitigation? Do I send SEAL Team 6 or whatever it is at the attackers or not?
Actually, since you bring that up, ideas for instrumentation, remember you're going to send them to the Flight Software Workshop. Can I add 2 references for people who are interested in this?
Of course.
This is like one of my favorite topics. One is a really old book called Normal Accidents. And it's just about how things get presented to people and then they blow up. It's just amazing. The other one is what every cyber person always says, what's your threat model? And so there's a book called Threat Modeling, and they're easy to read. Do you have it up there? Up there?
No, they're not an easy to read one.
It's of that nature.
One of many.
They're just super fun things to read because you learn how to do the engineering to make it right. Are there other questions? Oh, here. Oh.
So I'm curious if you know of, and if other people know of, are there, I mean, when we build a spacecraft, especially deep space, we rad hard, we soak it in a lab, radiation, vacuum chamber, all that stuff. Are we doing that for cybersecurity? I mean, given that I would argue it's probably more of a threat than radiation at this point for high-profile missions. And if so, what resources are there for soaking our equipment?
Is it fair for me to rephrase that as penetration testing?
Yes.
Are we penetration testing our systems? Not well, in my experience, that we can speak about, and there's 2 problems with that. One is you need a fully separate, for real testing, you need a fully separated system, and we don't usually have duplicates of the full system, right? If I want to penetration test your chip, well, I'm going to attack the ground data system. You got one of those in your thermal test? Oh no, we have this stubbed out play little test infrastructure. All right, well, I'm going to attack you through your authentication server. Do you have one of those in your test server? No. So it's very hard to do a full end-to-end attack thing without hitting the operational systems. Now, feel free to argue, but not with me because I won't take the other side, that why can't you have a full copy of your production system so you can beat on it? That would be nice. There are piecemeal, this gets back to that shingles question. You can take any piece of it and you'll have a story for why, well, we checked this chip for bad code, and we checked, did you check the interactions of your chips? No, not that I'm aware of.
That's a good point. Here.
So I'm aware of a basic tenet in security and engineering to use things in ways of which they were designed to be used. Are you familiar with any studies or references that I could consult around the robustness of common aerospace partitioning techniques against side channel or breakout attacks?
Not specifically, no. But I do know that I had segmentation, by which I meant partitioning, as it's just, that's exactly an example of security that pays for itself. If you build in all the defenses that an attacker cannot cross your boundaries, then think of all the programming errors that won't bite you, right? I've got lots of code that checks for a null pointer, right? Why aren't I checking that it's in RAM somewhere? It's not like null is the only bad, easily detectable, obviously wrong value for a pointer. There's a whole lot, there's a very small range of good values for a pointer. Why am I only checking one of the many bad? Why do I do that? I do that. I don't always do that. I'm inconsistent.
More comments? No.
Okay.
And so all these references will be online. You should pay attention. Thank you very much.
Good.